we are now going to cover the concepts of Chapter 10, which includes acids, bases, and equilibrium. Acids and bases are in substances that we use in everyday life. Our toothpaste, batteries, and even some food products, including soda, tomatoes, all of them contain in them acids or bases. The first thing that we're going to do in this chapter is name or know how to name acids and bases. So when it comes to acids, understand that we're going to have two types of acids. The first one is binary acids. The second one are called oxyacids. When it comes to binary acids, understand that these are going to be compounds that have a hydrogen ion followed by a non-metal. Okay? So, to give you guys some examples of binary acids, we have H2S, H2SE, HF, HCl, HBr, and HI. Now, when it comes to naming binary acids, understand that to build those names, we have to write the word hydro, followed by the stem of that nonmetal, followed by the ending, which is going to be ic acid. So, if we look at the example where we have HCl, as you can see, we're going to start by the word hydro. Then we're going to have the stem of the nonmetal present, which is chlor for chlorine. And we're going to end the word with ic acid. So the name for HCl is hydrochloric acid. When it comes to the oxyacids, as you can see, they are going to have a hydrogen ion followed by a polyatomic ion. So for those of you that were thinking, okay, I can be done with the polyatomic ions, we are not done with them yet. Okay? Now, when it comes to naming, understand that all you need to remember is the ending of that polyatomic ion. And remember that the list is in the back of the syllabus. So, for any polyatomic ion that ends in 8, you are going to substitute that 8 ending with ic acid. In any polyatomic ion that ends in "ite", then the ending is going to change to O's acid. As I've mentioned to you guys before, there's always exceptions to the rules. And the exception to the rule is outlined in the first bullet point. HCN will be the only acid that it does have a polyatomic ion. And when we name it, we're going to be using the rules for binary acids. So the name of HCN, which is the acid of cyanide, is hydrocyanic acid. So again, this HCN is the only acid that comes from the polyatomic ions that is not going to have this 8 to ic switch or this ite to os switch. We're going to name it like binary acids. When it comes to naming bases, understand that most bases are going to be compounds that have hydroxides. And as we learned in the beginning of the semesters, we are going to have, when we have compounds of hydroxides, a metal paired with hydroxide to make these bases. Now, remember, when it comes to the metal, we have two types. We have a type 1 and we have type 2 metals. In the case of hydroxides that have a type 1 metal, we're going to use the name of the element. In the case of the type 2 metals, we're going to use the name of the element plus, in parentheses, a Roman numeral for the charge of that type 2 metal. In the example that you guys have here, all of these are going to be type 1 metals. So that's why you see in the name of element. So for example, in the first one, sodium. And then we see the word hydroxide because that's the name of the polyatomic ion. Now, similar to what I expressed before, there's only an exception when it comes to bases, which is going to be NH3. NH3 is a base. And when it comes to its name, because it doesn't have hydroxide, that's why we're not going to include it in its name. From the common names of the covalent compounds, you know that NH3 is ammonia. And that's pretty much the only base that in this class we're going to study that does not contain hydroxide. Now we're going to move on to do some of the problems that we have on part 8 of our worksheet. I'm going to do specifically problems 1, problems 4, problem 6 in the type of the acids, and then I'm going to do 11, 12, and 13 when it comes to the bases. So when it comes to nitric acid, I know that this is going to be an oxyacid because it doesn't have the word hydro. Because it ends in ic acid, I know specifically that it's going to come from a polyatomic ion that ended in 8. So this specifically comes from nitrate. From the list of polyatomic ions, we know that nitrate is NO3 minus. So the chemical formula for this acid is going to be when nitrate is paired with hydrogen. So the final answer is going to be HNO3. On number 4, as you can see, we have a binary acid. And the reason why we have a binary acid is because we have hydrogen paired with a nonmetal. When we have that, remember that the name is going to start with hydro, followed by the stem of the nonmetal, that for bromine is going to be brom. And then the ending is going to be ic acid. So HBr, its correct name is hydrobromic acid. For number 6, we have hypochlorous acid. Because the ending is ose acid, I know that this came from a polyatomic ion that end in ite. So because I know that this is an acid, we're going to have an H paired with my polyatomic ion, that in this case is going to be hypochlorite, which its chemical formula is ClO negative. When we pair that with H plus, the chemical formula for that acid is going to be HClO. Then moving on to 11, 12, and 13. Here I have a type 1 metal and hydroxide. For type 1 metals, I'm just going to write the name of that type 1 metal. That for K, that is potassium. And then I'm going to write the word hydroxide because I have NOH. For number 12, I just talked about that exception. The chemical formula for ammonia is going to be NH3. And as you can see on number 13, we have another type 1 metal, which is magnesium. Magnesium has a charge of 2 plus because it lives in group 2A. When we pair it with OH minus, as we write the chemical formula, we're going to have magnesium. We're going to have hydroxide in parentheses, and it's going to have a subscript of 2. Now we are going to discuss how do we know that a particular compound is an acid or in a base, and what happens when they are in a chemical reaction. So talking about definitions of acids and bases, the first one that we need to be introducing is the first one that was proposed by Arrhenius. So Svante Arrhenius proposed that acids are going to be substances that dissociate in water and produce specifically H+. While bases, when they dissociate in water, produce hydroxide ions. Even though this definition works for many substances out there, not all are going to be producing specifically OH minus directly in the case of bases. So because this definition was a little bit more limited, a brand new definition needed to be introduced. That's why in many chemistry classes and even in biology, when we know of acids and bases, they utilize the Bronsted-Lowry definition for acids and bases. So according to the Bronsted-Lowry definition of acids and bases, an acid is a substance that donates a proton, and a base is a substance that accepts a proton. So in the bottom of the slide, as you can see, we have two separate chemical reactions. And for those that are interested on how Bronsted and Lowry looked like, you can see a picture of them in the slide. So as you can see, we have two acid-base reactions, and we even have the products that result from these reactions. In the reaction that we have on the left, we are reacting HCl and we are reacting water. As you can see, the reactant side of our reaction can be labeled as acid and base, okay? Now, when we have the product side of our reaction, we actually have to give those species that are formed after the reaction happened a name. So, since it has been established that HCl is the acid, so it donated a proton. Once it loses that proton, it's going to form that chloride ion. When water accepts that proton, it goes from H2O to H3O plus, because remember that it is gaining a positive charge, okay? I should clarify that every time I refer to an H plus, I call them protons, because commonly that's how we name them. So, as you can see, HCl is my acid. So, when HCl is acting as an acid, we have to give a name to that chloride ion. So, when we're talking about pairs, since HCl is the acid, that Cl minus or chloride ion that it is formed is called the conjugate base of the acid. In the case of the water, because water accepted that proton, the molecule that results from that water accepting that proton is being said that that is going to be the conjugate acid, okay, of the base in the reactant. Let's do another example to clarify this, just in case some people are still confused. In the next reaction, as you can see, we have in the reactant side ammonia as a base, water is acting as an acid. That means that since ammonia is acting as a base, it's going to accept a proton. So it's going to go from NH3 to NH4. That means that this ammonium ion that is formed is called the conjugate acid for ammonia. In the case of water, because water lost a proton, hydroxide, which is what is formed from where water lost that proton, hydroxide is considered the conjugate base of that water molecule. To review these concepts, we are now going to do some problems in Part B, C, and D of our worksheet. I am first going to focus on Part B and C. Part B reads, give the conjugate base for each of the following Bronsted-Lowry acids. What that means is that we're going to consider that these molecules in number 1 through 4 are going to be Bronsted-Lowry acids. So if something is behaving as a Bronsted-Lowry acid, remember, they are going to donate a proton. In other words, they're going to lose an H plus. So understand that when it comes to these molecules, if you have a neutral molecule and it loses an H plus, that's why I'm going to designate it as a minus H plus, overall the formal charge of that molecule is going to be negative. If you have a molecule that has a positive charge and it loses an H plus, that means that its overall charge is going to go to 0. Okay? So, if you have a molecule, that's pretty much what we have over there. So, I'm going to do, as an example, number 1 and number 2 for letter Part B. So, HI, as you can see, is a neutral molecule. When it loses an H plus, in other words, donates an H plus, we are going to form its conjugate base, which is going to be the iodide ion. For NH4, as you can see, this is a positive molecule. When this positive molecule loses an H plus, is going to go from 4 hydrogens to 3 hydrogens. And because it lost a positive charge, is going to go to neutral. I'm going to move on to Part C, which has to do with Bronsted-Lowry bases. As you can see in the instruction, it says, give the conjugate acid for each of the following Bronsted-Lowry bases. What that means is that if these molecules that we have in 1 through 4 in Part C are behaving like Bronsted-Lowry bases, they are going to accept H plus. That means that they're going to gain an H plus or a positive charge. So, for example, I'm going to do, when it comes to this, number 1 and number 2. If we have Cn minus, and is going to gain an H plus, then the overall formula now is going to be HCN. I should specify that is if your Bronsted-Lowry base starts at negative and you gain a proton, then is going to be now neutral. That's why HCN doesn't have a charge. If for example, on number 2, if you have 2 negative and then you're gaining 1 proton because there is 1 positive charge, then you're going from 2 negative to 1 negative. So in the case of number 2, since we have O2 negative, when we add the proton, then the resulting molecule is going to be OH negative 1. The other type of problem that we have in order to practice this is going to be identifying what is the acid, what is the base in any of the following reactions, along with what is the conjugate acid and what's the conjugate base. So for this problem, I'm specifically going to do number 1 and letter A and letter B. So in letter A, we have ammonia reacting with water, forming ammonium and hydroxide. And this is just to review, this was in the slide that we just discussed previously. But as you can see, NH3 gained a proton and became NH4. That means that NH3 is acting as a base. And if NH3 is a base, that means that the molecule that resulted in the product side from that base gaining a proton is going to be the conjugate acid. So conjugate acid, I usually write it down as CONJ for conjugate and then the word acid. So when it comes to water, water lost a proton. So that means that it reacted as an acid in the molecule that results after water has lost that proton, that is called its conjugate base. To keep the same labeling that I've done before, as you can see, water was an acid. This is its conjugate base. Ammonia was the base, and it gained that proton. Let's now go to part B, where we have water reacting with HCO3, forming CO3 2 negative and H3O plus. So, as you can see, water went from H2O to H3O plus. So that means that in this case, water gained a proton. So water is acting now here as a base. The molecule that results from a base accepting a proton, that is called the conjugate acid. So again, water is acting as a base. In this case, if water is the base, then the other compound has to be the acid. So HCO3 is the acid. And we can see that HCO3 negative 1 form CO3 2 negative. So that's how we know it lost a proton. Okay. So that CO3 2 negative is going to be the conjugate base of HCO3.